In geothermal system design, we've inherited a conservative habit from the hydronics industry, treating every pipe like it's made of steel. But in a large-scale HDPE loop field, that assumption leads to oversized expansion tanks, increased project costs, and wasted mechanical room real estate. Why? Because it ignores the dimension of time. Most modeling tools use the short-term modulus of elasticity for HDPE, roughly 150,000 psi. That's accurate for a 5-second pressure surge, but geothermal systems operate on a seasonal cycle. Over 60 to 90 days of summer heat or winter cold, HDPE doesn't just sit there, it creeps. As the material relaxes, its apparent modulus drops. The pipe becomes more compliant, effectively acting as a secondary expansion tank by increasing its own internal volume. The first step is to allow the system designer to specify several system parameters. Both the minimum and maximum entering water temperatures, to which our algorithm increases the range by 10 degrees to reflect average fluid temperatures in the system. The user then specifies the antifreeze type and desired freeze point, from which concentration and other fluid properties are calculated. The user then specifies the acceptable system pressure range, which typically may be 15 to 50 psi, however, can range as much as 0 to 100 psi. And throughout the system modeling process, virtually every foot of pipe is defined by material, diameter, and length. Each pipe material has their unique set of characteristics that affect expansion due to both temperature and pressure. It is clear that all the plastic materials have a significantly lower modulus of elasticity as well as larger thermal expansion coefficients. Therefore, conventional hydronic industry practices are not appropriate. GeoDesignPro automatically applies temperature derating factors. Since HDPE's stiffness can drop by 25% or more when moving from 73 degrees Fahrenheit to 105 degrees Fahrenheit, our algorithm recalculates the system's net volumetric capacity at every degree. When we look at the standard expansion tank formula, we often see it as a rigid calculation. But for the geothermal engineer, this equation represents a dynamic, living balance between fluid physics and polymer science. Let's look at the top of the fraction. First, we have delta V fluid. This is the unavoidable consequence of thermodynamics. As our ground loop moves from its winter minimum to its summer peak, the fluid expands. In a large-scale system, this expansion can amount to dozens or even hundreds of gallons. But here is where geothermal design departs from traditional hydronics. Minus delta V pipe. In a steel or copper system, this value is effectively 0. But with PE 4710, the pipe is an active participant. As the temperature rises, the pipe doesn't just hold the fluid, it expands to accommodate it. By using the long-term apparent modulus in our software, we accurately calculate how much room the HDPE creates for itself over a 90-day season. Every gallon the pipe absorbs is a gallon the expansion tank doesn't have to. This subtraction is the key to preventing oversized, over-budget mechanical rooms. Now, let's look at the bottom. Acceptable pressure swing. This is your safety margin. It's the delta between your system's cold static pressure and the hot setting of your pressure relief valve. A system with a narrow pressure swing, say only 10 psi, forces the expansion tank to do more work, requiring a larger vessel. By widening this swing or optimizing our starting pressures, we can further refine the footprint of our equipment. The takeaway is simple. If you don't account for the expansion of the pipe, you are only solving half the equation. Our model uses this full volumetric balance to ensure that your expansion tank is sized for the real-world behavior of HDPE, not the theoretical rigidity of steel. It's not just about fitting a tank, it's about understanding the synergy between your fluid and your field. Here's an example of a sizable system. If we go to zones, you can see we have approximately 75 heat pumps in this system with a heating load of 927,000 BTU and a 77-ton cooling load. If we go to the Loop Field tab, you can see we have 3 groups of 11, so 33 bores, close to 500 feet deep. Distribution piping has all been laid out. All the heat pumps have been identified and how we're feeding them. So all the interior piping is included. And then we go to the Flow Center tab, where the expansion tank sizing is located. It provides a system summary, the total volume in gallons, the design fluid temperatures, and we take the extreme minimum and max, and we add 5 degrees to the max and subtract 5 degrees from the minimum. And that allows us to get closer to an average temperature in the system. It will predict based on a minimum setting, in this case 15 psi, it will predict that the expected winter peak will be as high as 29.2 psi. And it tells you if you're charging this on startup, where you're in the middle of the temperature range, say 62-degree water, that you want to target the system pressure to be 21.3. If the fluid is warmer, you will want to lower startup pressure accordingly to prevent excessive winter pressure. In this case, the range we will allow is 15 to 50. If we tighten up that range, we start dialing it down. We want to get it down to, say, 30 psi. Well, we still don't need an expansion tank, but as soon as we start narrowing our allowable pressure, the expansion tank requirements keep going up. All the way up to a 1 psi swing, you'd need a very sizable expansion tank. So we typically allow 15 to 50 is, I think, a good design range, and you're comfortably below needing any expansion tank on this system. Hope you enjoyed our deep dive into one of the facets of GeoDesignPro, which is currently available to everyone at no cost. Go to geodesignpro.com, create an account, and let us know what you think, as well as features you would like to see added or improved.